We have our third talk for this morning before tea. There's no pre-tea today because we're not talking about pre-Riesz spaces. So our third speaker is Damla, and she will be talking on tensor products of Riesz subspaces. Now, where are you going to attach this? Are you keeping your scarf on?
Yes, it's cold. So I am going to talk about the tensor products of Riesz subspaces. First, let me mention shortly about the history of tensor products a little bit. So it starts with Fremlin in 1972. So Fremlin constructs the tensor product of Archimedean Riesz spaces, and he does this using representation of spaces of continuous functions. He represents these spaces as the subspaces of continuous functions on topological spaces X and Y. And after Fremlin, many people studied tensor products of different spaces. After that, Grobler and Labus-Cagne did another construction of Fremlin tensor products. He used Dedekind completions. And Ono and Anke studied the Archimedean partially ordered vector spaces tensor products. So this, in 2017, Azuzi, Benamor, and Jaber, they published this paper about tensor products of F algebras. So they show that the tensor product of two F algebras is again an F algebra. This was done by Benamor also for D algebras, but we couldn't make it for almost F algebras. So now, yes, so after Grobler just recently defined the Dedekind complete tensor product. Yeah, he defines it like for two Riesz spaces E and F, he defines it as the Dedekind completion of the Riesz tensor product. So our question is, the tensor product of ideals or bands are again ideals or bands. So this question was first introduced in this paper of Azuzi, Benamor, and Jaber. So this will be our focus. And here is how I'm going to follow. First, I will give some short preliminaries from Riesz space theory to recall, and Fremlin tensor product construction, and then the Dedekind complete tensor product of Grobler. And then I will tell you about the results for the tensor product of ideals, which we do for firstly principal ideals and then ideals, and then the results concerning the principal bands and projection bands. Okay, so here are some basic, I know you all are familiar with the basic concepts, but to recall, so if A is a non-empty subset, then the disjoint complement is an ideal and a band in E. And the disjoint complement of the disjoint complement of A is the band generated by A. And if A is a band, then it's equal to the second disjoint complement. So a band is called a projection band if E is written by the direct sum of this B and the disjoint complement of B. And a Riesz space is called regular if the embedding of the Riesz subspace of E preserves the arbitrary suprema and infima. And this, every positive vector, we know, is a weak order unit in the band it generates. Yeah, some basic theorems that will be useful. Every order dense Riesz subspace is a regular Riesz subspace. and every ideal is order dense in the second disjoint complement. And it is order dense if and only if the disjoint complement is 0. And this is important to remember that in a Dedekind complete Riesz space, every band is a projection band. So we have this lemma that will be useful in later, but it has its own importance also in itself. So if we take a positive element in a Riesz space, then the principal band generated by this element is order dense and majorizing in the principal band generated by U in the Dedekind completion. So let me give you the construction of Fremlin quickly. So if E and F are Archimedean Riesz spaces, then there is a G and a bimorphism phi, such that whenever H is Archimedean Riesz space and psi from E Cartesian F to this H is a Riesz bimorphism, then there is a unique Riesz homomorphism T from G to H, such that this composition holds. And phi induces an embedding phi hat from the algebraic tensor product of E and F into G. And this is relative uniform density. This denseness is that we take 1 omega from this G, then there exists x0 and y0, such that for every epsilon there is an element we can find in the image of phi hat, such that this inequality holds. So, yeah, if omega is if we take omega positive, then there exists positive x and y, such that this inequality holds. Such space G is called the Fremlin tensor product, and it's unique. And we will denote it by tensor bar, E tensor bar F. And the Fremlin tensor product also has these properties: positive relative uniform density. I don't know what is it. So positive universal mapping property and boundedness. So in this construction of Fremlin, the tensor product is not order continuous in general. Phi here. Yes, okay. So it is not in general order continuous, and we need the Riesz tensor product to be the Dedekind complete for order continuity, which was proved by Grobler recently. So in the Dedekind complete case, we have the order continuity. But even if E and F are Dedekind complete Riesz spaces, then the Riesz tensor product is not always Dedekind complete. So for this, we have an example which was introduced by Grobler. So if we take the algebraic tensor product of C of X and C of Y, this is uniformly dense in the space of continuous functions on the Cartesian product of X and Y. This is by Stone-Weierstrass theorem. And the relative uniform completion of the Fremlin tensor product is a dense subset of this space. And this implies the relative uniform closure, the relative uniform closure of the Fremlin tensor product is dense in C of X times Y. And yeah, and then it means they are equal, and this is relative uniform complete. So if the Fremlin tensor product is Dedekind complete, then it will be equal to this space, and so this is Dedekind complete. But if this is Dedekind complete, then X Cartesian Y is a compact Hausdorff extremely disconnected topological space. However, we know that if X and Y are extremely disconnected, then X Cartesian Y is not always extremely disconnected. So that's why, in general, we can say it is Dedekind complete every time. In general, it is not general Dedekind complete. So this Grobler defined the Dedekind complete tensor product because it is order continuous in the Dedekind complete case. And here is his construction. So if we take E and F, two Archimedean Riesz spaces, the tensor product, which we show with the delta, tensor bar delta, this is the Dedekind complete tensor product. It has these properties. So algebraic tensor product is a vector subspace of the Fremlin tensor product, and the Fremlin tensor product is the Riesz subspace of the Dedekind complete tensor product. And if G is Dedekind complete Riesz space, and we have psi from E times F to G, order continuous Riesz bimorphism, then we have an order continuous Riesz homomorphism tau from the Dedekind complete tensor product into G, such that this composition comes. And the Dedekind complete Riesz subspace generated in the Dedekind complete tensor product by the algebraic tensor product will be Dedekind complete tensor product of E and F. And additionally, these properties Dedekind complete tensor product has is order denseness. Order denseness in this sense, boundedness, and positive universal mapping property, as in like similarly in Fremlin's construction. So our problem is tensor product of ideals is again an ideal, or tensor product of band is again a band. So we have partially an answer to all these questions. So for the Riesz tensor product, this is not true, which was shown with a counterexample for ideals only. And for the Dedekind complete tensor product, it is true, which I will show you in our results. And for the ideals case, the Riesz tensor product is not true. And Busquets and Thorne recently presented this counterexample. So, okay, we take piecewise polynomials here. And yeah, we take piecewise polynomials and polynomial functions on the segments. And we suppose we consider the Archimedean Riesz space as this space on 0 to infinity. And if we take two elements x and y as p of x and q of y, then this will not be an ideal, because if we can find an element smaller or equal than x times y, but this element is not in this space, so it is not an ideal. Okay, if we come back to our question, now we will consider E and F as Archimedean Riesz spaces. And we have this following lemma. We proved it by using Yoshida representation theorem. It says that if we take strictly positive elements, two strictly positive elements in E and two elements in F, the algebraic, the elementary tensor X tensor Y, smaller or equal than X prime tensor Y prime, then in this case, X will be in the principal ideal generated by X prime, and Y will be in the principal ideal generated by Y prime. Okay, in the next propositions, we give the order denseness result. Order dense, we say that the Riesz tensor product of principal ideals is order dense Riesz subspace of the ideal generated by this elementary tensor. Yeah, here we give also the order denseness for the principal bands. Okay, if we take two principal bands, BE and BF, generated by E and F, then the Fremlin tensor product of these principal bands is order dense Riesz subspace in the principal band generated by this element in Riesz tensor product. And this next proposition is is a generalization of Grobler's result. Grobler assumed the Riesz spaces there as Dedekind complete Riesz spaces, but we eliminate the Dedekind completeness here, so it's more general. If we take two Archimedean Riesz spaces and weak order units from these spaces, E and F, the elementary tensor E and F, E tensor F, is a weak unit for the Fremlin tensor product. So this is, yeah. So firstly, we show that here, okay, let's take two Riesz spaces and positive elements from in E and F. The principal ideals will be EE and FF. So we have the principal ideal generated by E tensor F in the Dedekind complete tensor product. Okay, this is equal to the Dedekind completion of the principal ideal generated by E tensor F in the Fremlin tensor product. And then we can prove this theorem. The Dedekind complete tensor product of the principal bands, principal ideals, EE and FF, is equal to the principal ideal generated by E tensor F in the Dedekind complete tensor product. So we yield this corollary. So if the Fremlin tensor product is Dedekind complete, then this Dedekind complete tensor product of principal ideals will be an ideal in the Fremlin tensor product. Okay, so now this is we did it for the principal ideals, and now we have this important result for the ideals and their Dedekind complete tensor products. So if E and F Riesz spaces, and if we take A and B, two ideals from E and F, then their Dedekind complete tensor product is an ideal in the Dedekind complete tensor product of the bigger spaces. And we can have this corollary after this. If it's the Dedekind complete, the Fremlin tensor product, then the Dedekind complete tensor product of ideals will be an ideal in Fremlin tensor product. Okay, now we come to the case for principal bands. Okay, here we say that if we take two principal bands, BE and BF from E and F, generated by E and F, then for every positive element in the band generated by E tensor F, we can find a U in the Dedekind complete tensor product of these principal bands, such that this inequality holds. And this means the Dedekind complete tensor product of principal bands generated by E and F, it is majorizing in the band generated by E tensor F. So we show that it is majorizing, and then we show that it is actually equal to this band. So if we have, okay, BE and BF, yeah, this is just equality. Nothing more to say. Okay. Okay, and we have, if we have two projection bands, this also we did for the projection bands of the principal bands. If we have A1 and A2 projection bands, then the Dedekind complete tensor product of these projection bands is again a projection band in the Dedekind complete tensor product of ENF. And if we have them as Dedekind complete, so it will be the Dedekind complete tensor product will be a projection band since in Dedekind complete we have every band as projection band. Okay, so we did it for principal bands and projection bands, but it is still open that if it's true for bands, just bands. So is the Dedekind complete tensor product of bands is a band, is yeah, still open. And here are my references. Here you can find the construction of Fremlin and Grobler and Labus-Cagne construction of Fremlin tensor product. Yeah, the tensor product of F algebras, where we find these questions. And this is the Dedekind complete tensor product definition was in. And this is where you can find the counterexample for the ideals, that it is not an ideal tensor product. Okay. Thank you.
Thank you. Are there questions for Damla? Yes.
Thank you for this nice talk. It's not a question, but it's a commentary. If we now we have the tensor product of two ideals is an ideals in the tensor product Dedekind completion.
Yes.
If one of this factor, one of the ideal is prime or is maximal, what we think about the tensor product, but this is commentary. You can think about this. If one of the two factor has some additional structure, what we can get in the tensor product of. Thank you.
What's your next 5 years?
I don't know. It's 5 or yeah.
Good, thank our speaker again. Do people have to check out at 11? Yeah. So